This lecture is entitled For You No Charge, and it's going to introduce you to the concepts of voltage and current. So, people who enjoy meetings should not be in charge of anything. It's a different type of charge, but the sentiment holds. So, the purpose of this is for you to be able to understand the sources and types of voltage, that you be able to understand the safety guidelines concerning current and voltage, and that you be able to calculate electric current and also calculate voltage as well. First off, what we already knew. We already knew that circuits require a voltage source and a path for charge to flow in order to function. We knew that already from the previous lecture in the labs that we've done so far. What we learned in the lab, though, is that the voltmeter is a measure of potential difference. It has to be wired in parallel with whatever you're trying to measure. So, for example, if I'm trying to measure the voltage of this resistor, I have to connect it to either side of the resistor. Okay, and what that would look like is this here. That's the voltmeter connected to it, and that's the symbol schematic. You should also know that this voltmeter measures the push of charge and has a very, very high resistance. So if you were to put the voltmeter here in front of the resistor, okay, you would be affecting the circuit a great deal. We also found out in the lab that we have an ammeter. The ammeter has to be wired in series, and it measures how much charge is moving through it. So you have to put the resistor in series with the ammeter because the current that goes through this is the same as the current that goes through that. Now, what we learned in the lab is that the voltage source is used by a device along the way. So we may start off with something like 9 volts here. So you can go ahead and make that smaller. We may start off with something like 9 volts here, but by the time we get to the other end of the battery, it's 0 volts, and that voltage is used along the way. Now, voltmeters, as you see it's wired here, has to be wired in parallel. And an ammeter has to be wired in series, as you see here. One important thing that you learned was the electrical current was the same everywhere on the circuit that you measured it. Now, that's going to come into play a little bit later, but for now, whenever you have a series type circuit, the electrical current is going to be the same everywhere. So we look at the water analogy. We decided that voltage was the push that moves the electrons through the wire, and we did say we're going to move electrons. That's kind of a misnomer, but it's analogous to gravitational potential energy. So whenever you have gravitational potential energy, you take a book and you rise it above the surface of the earth, and what you do is when you let this thing go, whenever you release it, it will fall to the earth because it's attracted to the earth because of gravity. The same basic thing is happening with a voltage source. You have a positive terminal and you have a negative terminal. And they're attracted to each other, but they're physically separated by a barrier. So they can't cross over. But if I connect a wire in between, now there is a potential for these things to move back and forth. And so the negative charges can move through the wire to the positive end of the battery now. So voltage refers to the amount of energy that each one of these little charges has. So charges. Batteries have a positive and a negative end. So we've got a positive terminal and a negative terminal. The work that is required to maintain its position is considered to be the electric potential energy. Okay, voltage is the potential energy per charge. So we discussed this real briefly already in the last unit. We said that the potential energy is how much you have to, if you have a positive charge and a negative charge, how much work do you have to do on this negative charge to keep it from being attracted to the other side? The major sources of voltage that we'll talk about are batteries, wall outlets, dryer outlets, Van de Graaff generators, and even your balloon on hair. The most common one that you'll look at is the outlet and the battery. We'll talk about batteries here in a second, but the dryer outlet and your traditional outlet are very similar but also very different. They both provide the same type of voltage but different values. That's why these plugs are incompatible. If you were to look, this would be a 240 volt plug, while this is a 120 volt plug. So it produces twice as much voltage. If you're pushing it with more voltage, that could be a safety concern because you're pushing it through something that it's not designed to handle. So electrical outlets, the traditional American outlet operates at 120 volts and 60 hertz. The 120 volts is telling you how much it's pushing through. And the 60 hertz is telling you how many times it's flipping back and forth. We'll get to more on that a little bit later. But you do need to know this. Okay? And a traditional European outlet operates at 240 volts. So you can't use American devices and outlets in Europe because it operates at a different voltage. It will be a fire hazard if you were to plug an American device into a European one. But the frequencies of oscillation are different as well too. So this one is operating at 50 hertz and this one is operating at 60 hertz. Okay, that's not really a whole lot of difference at this point. It just tells you the amount of times it's going back and forth. It does have implications if you think about it in terms of a light bulb, but we'll get to that a little bit later. Now, why is plugging in a 120 volt appliance into a 240 volt outlet dangerous? Because you have too much voltage, and that too much voltage pushes the charge too much and can cause a fire. Can definitely ruin your electronic devices as well. So here are some common batteries that you see. This right here is a car battery, and generally speaking, they're between 12 and 24 volts, depending on your type of car, truck, whatever. They can be bigger, but generally it's between 12 and 24 volts. This is a 9-volt battery, and this is commonly used in most physics classes, and then also you have a 1.5 volt battery. Any cylindrical battery, C battery, D battery, AA, AAA, is going to operate at 1.5 volts. So these are just some common batteries that you should see. You can take batteries and you can figure out what they are. They're basically two different chemical solutions. If it's a wet cell battery, there are two different solutions, and these two different solutions consist of positive and negatively charged ions. They're usually separated right here. And what happens is you have a chemical reaction occur that allows the electron to be produced and move to the other side. Okay, that's generally what happens when you have a wet cell battery, and it's the origin of the term battery acid. Okay, you generally have an acid on one side and then something that's not quite as bad on the other side, and because of that, it produces an electrical current. Incidentally, that's why if you plug one into the wall, you can actually reverse the reaction and you can recharge the battery. Voltage is an additive thing. So if you take the negative end of the battery and the positive end of the battery and you combine it with the negative end of the battery and the positive end and so on, the voltage is additive. So it goes up to 4.5 volts. Now, if you were to do something like this, where you have a battery that looks like this and you go with a battery that looks like this, those batteries will actually cancel each other out. So if you've ever tried to put batteries in a remote control or something and it didn't work because you put the batteries in wrong, it required a certain voltage in which to operate, and because of the way that you put them in, say we'll put this one back in like this, because of the way you put it in, these two canceled out and you only got 1.5 volts. So the direction of the batteries are really important. In addition, if you notice, what we've done is we've wired these batteries in series. Whenever you wire batteries in series, that's when the voltage is additive. Now, if you were to do something like this, and there are circumstances in which people do this, if you have batteries and you were to wire them in parallel like this, and then you have your device, when they're in parallel like that, the voltage is still that 1.5 volts. Okay, so it's the 1.5 volts for this battery, and it's 1.5 volts for this battery, but you can't add them. The purpose of putting the batteries in like this is to get them to last longer. So what is the effective voltage of this particular picture? If you look, you have 1, 2, 3, 4 cylindrical batteries, and if you look, they're going in opposite directions. So because of that, I say I have 4 1.5 volt batteries that are all additive, or about 6 volts. It says, what is the voltage of this picture? Once again, you see these are oppositely charged, and then it goes to here, and these are oppositely, and these are opposite, and these are opposite. Each one is 1.5, so I'm getting 3 volts here, 3 volts here, 3 volts here, and 3 volts here, for a total of 12 volts. So now let's talk about the danger high voltage sign. So the first thing that you want to realize is that voltage by itself is not dangerous. Now, before you go and grab a danger high voltage power line, Let's stop and let's rehash this. It says danger, voltage by itself is not a danger, but voltage turns into electrical current whenever you have some sort of resistance or lack of resistance there. So because of that, those two things combined can actually lead to electrical current, which is dangerous. A danger high voltage sign, though, is not nearly as accurate as a danger electric current sign, because electric current is the health hazard that you have there. So we're going to extend voltage a little bit. We're going to talk about where the idea of voltage comes from. Voltage, which is V, comes from the electric potential energy divided by the charge. We measure voltage in the unit of the volt. But really what a volt is it is a joule per coulomb. A joule per coulomb. So we can measure voltage with a voltmeter. Okay, we can look at charge with an electroscope, and that would allow us to calculate the electric potential energy. So let's take a look at this example. Another example of this, it says you have a single electron that has a charge of 1.6 times 10 to the negative 19th. That's my Q value. Q equals 1.6 times 10 to the negative 19th. Okay, then it says how far away would the charge produce a voltage of 9 volts. So I'm looking at a charge of 9 volts. And I'm trying to solve for the distance. And at this point you look at this and go, I have no idea. The formula is voltage equals energy divided by charge. But let's think about it for a second. Okay, I've got electric potential energy. But another term for that, remember, you can take any energy, depending on the situation, and turn it into work. And work is really force times distance. So what I could do is I could say voltage equals force times distance divided by charge. And that would be really helpful, except for the fact that I don't have force. Now I've got this distance term, which is really helpful, but I still don't have force. So how am I going to do this? And it's not really what I'm trying to solve for. So what I'm going to do is I'm going to expand this a little bit further. We're talking specifically about one type of force. And that one type of force is the electrostatic force, which we covered last unit, which is equal to K Q1 Q2 over D squared. That's my F term, because that's the electrostatic force, times D divided by Q. Now it looks like a lot, but look, the D is going to cancel out, leaving only the D. Cancel it out with the squared term. This Q is going to cancel out with one of these Q terms. It doesn't matter which one it is. And then finally what you're going to have is voltage is equal to K, which I know is a constant, Q, which I have, over D, which is what I'm trying to solve for. So the last kind of iteration of this is distance is going to equal to KQ over D, which in our case, when we plug in our numbers, we would get, distance equals 8.99 times 10 to the 9th times Q, which is 1.6 times 10 to the negative 19th, divided by, and this would be, voltage, which would be 9. When you plug all that into the calculator, you would get a distance of 1.6 times 10 to the negative 10th meters. So in order for a single electron to generate a voltage of that of a battery, it would require it to be 1.6 times 10 to the negative 10th meters away from whatever it's trying to produce that voltage on. So it has to be almost the size of an atom. So that's not realistic. That's why batteries have more charges in them than just the one. So how much energy is required for a hairdryer to move an electron, so once again we're dealing with an electron, down a wire when plugged into a standard American outlet? Now remember, you're supposed to know that a standard American outlet is 120 volts. And you're trying to figure out how much energy is required to move an electron. An electron is 1.6 times 10 to the negative 19th, and the reason I know that is from the previous example. So now I can use the formula V equals EPE over Q, realizing that energy is energy. So because of that, I can plug in, I would say 120 equals Forgot to say that EPE is what I was looking for. 120 equals EPE over 1.6 times 10 to the negative 19th. So the amount of energy stored or used when moving a single charge down a wire is just a very, very small value of 1.92 times 10 to the negative 17th joules. Now remember, that right there is for moving a single electron down the wire. If you're talking about plugging something in, you're talking about lots and lots and lots of charge, not just a single electron. This one right here says you have a 12-volt battery that is capable of providing 10 joules of energy. What is the charge moving through the wire? So once again, we have a voltage of 12. We have the electric potential energy is 10 joules, and we can solve for Q. So we have V equals EPE over Q, and in our case we have 12 equals 10 divided by Q. We would rearrange and we would get Q equals 10 over 12, which in our case would be, it would end up being 10 over 12, which is approximately, we'll call it 5/6, and you can take that and you can turn it into a decimal. But that right there represents how much charge is moving through the wire. Now, this is a lot of charge. Okay, charge is generally dealt with in a very, very, very small amount. So this is an exceptionally large amount of charge. Charge is measured in coulombs. So let's continue our water analogy for electrical current. Electrical current is like water flowing through a pipe, but instead of water, we're talking about charge. So electrical current is how much charge is moving through a wire. It's not really how much, it's really the rate at which charge moves through the wire. You can think about it as velocity for the charge, because you have two types of current. The first one is called direct current, and that's when the charge moves in a single direction. And I say moves because it's not really moving, but a battery is what provides a direct current. It's a flow of energy or a flow of charge as it moves through the wire in a continuous direction in one way, from the positive to the negative terminal. And a battery provides that direct current. Now, alternating current is a little bit different. Alternating current is where the charge moves back and forth, and back and forth, and back and forth, as depicted by this graph. It's kind of a sine graph if you're used to that from math. This is what you get from household appliances. Household appliances give you alternating current because that's what you plug it into them. Now, there's a big difference between alternating current and direct current that came about, and this debate between Edison and Tesla actually defined our electrical system as we know it. Tesla used to work for Edison a long time ago, but they had a lot of friction between them. Edison was the owner of the company. He had numerous patents, and Tesla was kind of an upstart. He was a brilliant engineer, and Edison, he came to work for Edison in New York, and they quickly had difficulties in terms of their idea for electrification, which is trying to bring electricity to the masses. Edison was a big proponent of DC, which is direct current, and Tesla was a big proponent of alternating current. Alternating current has some advantages in the sense that it can be moved over long distances. And that's the biggest advantage, which is the reason why we use alternating current today. That and the fact that you can increase and decrease the voltage relatively easily. Edison, on the other hand, believed in direct current. And the reason why he believed in direct current is because this is the ultimate what devices use. So devices generally use direct current. The problem with direct current is it only operates over short distances, and since it only operates over short distances, you have to have several power plants throughout. You can't put one power plant outside of a city and bring power to it. You have to have multiple within the city itself. So because of that, we use alternating current. But the story doesn't stop there for some of you who are interested. Edison wanted to show the dangers of Tesla's system of alternating current, and he wanted to show how high voltage was potentially deadly. And so what he did is he built this device that was shown how high voltages can electrocute things. Specifically, you can look up the story of Topsy the elephant if you're interested. But what he did at this point is some government officials saw it and said, hey, can we use that as a method of execution for our criminals? And that's where you get the idea of the electric chair. From Thomas Edison trying to show how dangerous Tesla's invention of alternating current is. Now, you have to go back and forth between AC and DC. And a lot of times you see this on, on a device like an Xbox or a PlayStation. They have a big box on the back of it. And on the back of that box it says AC DC adapter. And that right there is saying it takes the alternating current and it adapts it to a direct current. So you should know the difference between alternating current and direct current and kind of why they're both important. So what are the advantages of each? Well, we've talked about these. Alternating current is the fact that it's got long distances and you can change the voltage. Direct current that's what we use. Okay, but the disadvantage is you can't send it over a long distance. So conventional current. Conventional current is it's a way that we use to explain things. We're assuming that positive charge is what moves through the circuit. Now we know that's not right. Okay, in fact, some people will say, well, it's really electrons that move through because protons can't move. It's not really that either. Current is really just energy moving through the wire, not really protons and electrons and those sorts of things. So it turns out that if you have an electron in the wire, it does move a little bit, but it moves about 1 centimeter per second. Okay? If you had to flip on a light switch and wait for an electron to get to a light bulb from the voltage source, you're talking about having to wait 10, 15 minutes, 20 minutes, depending on the size of where your circuit breaker is, in order to get electricity to that particular light bulb. Instead, when you flip the switch, it immediately turns on because the energy is what lights up the light bulb, and it's what's traveling very, very, very fast. Okay, so we are going to use the term conventional current, in which we are assuming that it is positive charge that moves through the wire. No, that's not really the case, and this is a way of making it simpler to build a model with. Danger current. We've already talked about this, but voltage by itself isn't dangerous, but voltage turns into current. Current is dangerous. A current of 0.4 amps across your chest is enough to stop your heart or start your heart. That's how an automatic external defibrillator works, or an AED device. Okay, it uses an electrical current to try and restart your heart. Electrical safety. So there's some rules that we're going to adhere to, and you've probably seen these already in the lab. But number one is you will always leave the voltage circuit off when manipulating the circuit. If you need to take this resistor out and you need to put something different in, you turn off the circuit and then you remove the resistor. Then you put the new thing in and then you flip it back on. Okay, if you have to work with with electricity, with high voltage, you are to use gloves with a high resistance. Now, this is probably not going to be the case in your labs. You're going to be dealing with labs that have extremely low voltage and very low currents. If you have any sort of sweat or perspiration, you need to wipe that sweat away so that it's not on your hands. Whenever you have sweat on your hands, it makes it more likely that you can get an electrical shock. And the last thing is, if you are working with high voltages again, it's good to work with one hand in your pocket. And the reason why is, if you have somebody and they've got a hand right here, and I'm a great artist, okay, and they've got a hand right here, if they're working with a circuit here and working with a circuit here, okay, the current would go through your chest to the other side. If you have this hand in your pocket and only work with the circuit here, you're not going to get that same flow of charge across your chest. So it's called the one hand in your pocket rule, but these are some good electrical safety rules to adhere to. What can you do to reduce the risk of electric shock when working with electricity at home? We just talked about it. You can use the safety rules that are there. Okay, specifically, you can shut off the electricity at the circuit breaker. Okay, that's where you can shut off the electricity. So if you're ever replacing outlets or switches, go to the garage or wherever your circuit breaker is and flip off the electricity to that room or the house, depending on what you want to do, and then start to work. Okay, make sure you wipe away all your sweat, put one hand in your pocket, wear gloves, specifically highly insulating rubber vulcanized gloves is really what you're looking for, not just Hey, they like me. My hands look pretty, gloves. Okay. Next, you have an electrical current extension. So this right here is where the term current comes from. And current is referred to as I. Okay? Current is measured in amperes, or amps is really for short. We usually call it just A, and sometimes there's a circle on top depending on what book you're looking at. What current refers to is the amount of charge, or the change in charge, or the charge that flows past a certain point divided by the amount of time that it does. We can measure the current with an ammeter. We can measure time with a stopwatch. We can measure electrical charge with an electroscope. So we can measure all of these. Really the new one, though, in this case is the electrical current. So if you look, it says, oh, this is chemistry. Determine the current if 3.45 grams of ionized chlorine flows past a certain point every 200 seconds. And you're thinking to yourself, it has been at least a year since I've done this, but we can figure this out. The current is equal to the charge divided by the time. You have 3.5 grams of ionized chlorine, which means you have 3.5 grams of chlorine. You can say that in 35, we'll say 0.5 just for kicks, 35.5 grams of chlorine, you have 1 mole of chlorine. And now you're thinking to yourself, I did not sign up for this mole stuff again. In 1 mole of chlorine, okay, you have 6.022 times 10 to the 23rd chlorines. And then finally, in each 1 chlorine, you have 1 extra electron because it's chlorine minus, which tells you that you have 1 more electron than you do of anything else. And now, based on the stuff that we learned in our last unit, you can say that Q equals NE, or the charge is equal to the number of charges times the E value. Well, in our case, this value right here is the N. And then we have our E value, which we can calculate, or we don't calculate, it's a constant, is 1.6 times 10 to the negative 19. When you take this thing and you run it all the way across, what you end up with is 5.94 times 10 to the 22nd excess electrons, times the charge per electron is 1.6 times 10 to the negative 19th, and you get an excess charge of 9,504 coulombs. Okay, that's a lot. But now you take that and you divide it by the 200 seconds, and you get I equals 9,504 coulombs divided by 200 seconds, which is approximately 47.5 amps. In this one, it says a 400 milliamp current across the chest for 1.25 seconds can be lethal. Determine the charge that flows through your heart during this interval. So we're trying to use the idea of I equals Q over T. In this case, you have 400 milliamps, which is 0.4 amps. You should be able to convert from milli to anything at this point. So now we plug in and we say I have 0.4 amps, which is my I. I have my time, which is 1.25, and I'm trying to solve for the Q value. I've got my formula. I plug it in. I get 0.4 equals Q divided by 1.25. Multiply both sides, and when you do that, you get 0.5 coulombs, which is a capital C, equals the charge. And our last example says how much charge flows past a certain point every minute when subjected to 2 amps of current. So we're going to do I equals Q over T again. And we have our I is 2 amps. We have our Q is what we're trying to solve for. And our time in this case is 60 seconds. You should know that 1 minute is 60 seconds. So now we plug in our numbers. We would say 2 equals Q over 60. Multiply both sides by 60, and when you do that, you get 120 coulombs equals Q.